Hello and welcome. In part three of topic five, we would like to take a few more numerical examples to demonstrate the generality and the significance of generalized functional observers. So we consider this class of time delay system where we estimate a generalized functional of this time delay system. And so we take example two, which is from this reference here. Now, in this reference, which is this paper, where we demonstrated that uh, stack observer with estimated instantaneous of the unmeasurable stack variables does not exist when we consider an observer without internal delay. And we design an observer, which is a delay stack observer, to estimate the unmeasurable stack variables. So we have a time delay system with matrices A and ID and B and C given in this reference here. So if we look at the actual notation of it, I is actually I bar 1, 1. So this is the time delay system. And ID I bar D 1, 1. So we take the same matrices in this reference. Now, according to the analysis in this paper, it showed that the method by Howe and his co-authors, which is reference 15, which is this paper. This is the one based on the output injection approach. Now, the existent condition there was not exist, were not existed because of the uni or column unimodular. And so the transformation is given as follow. There are some stack variables that when we apply them to the original system, we can transform that into the new coordinate. And then it is possible to design not the instantaneous unmeasurable stack variables, but the delay unmeasurable stack variables, 3 of them. So in this example, we have 2 output measurements. So the first 2 stack variables are directly from the output measurement vector, but there are 3 unmeasurable stack variables corresponding to the third and fourth and the fifth stack variable. We can't design an instantaneous stack observer for them. So we have to rely a delay stack observer. Now, so let's go into our analysis. So according to the method by this reference, it's not possible to estimate them instantaneously. And even if we aim to, let's say, want to design an instantaneous stack observer to estimate the unmeasurable stack variables, using other existing methods in the literature, for example, in this reference, where the observer structure is given without internal delay. So there is no ND in this term here. And if we test the condition, it's actually satisfied, but it's resulted in an unstable observer error dynamic equation, where the eigenvalues of this matrix is actually unstable. And so that is why if we want to estimate the the three stack variables here instantaneously using an observer without internal delay is not possible due to a existence of a fixed unstable pole in there. And How Muller, no, how and other co-authors methods actually does not work. So that's why it demonstrated in this reference that we can actually estimate not the instantaneous like variable, but the delay one of the unmeasurable like variables x, 3, 4, and 5. And so this actually this estimation of the delay stack vector actually is, is a small subset of the generalized functional that we consider in our observer for the generalized functional here. Okay, so if we then use our method, this is basically we are estimating this generalized functional for a particular case where F is a zero matrix and FD is this non-zero matrix, which is basically consisting of the last three delay stack variables. Okay, so you can see the unified framework that we are having in this generalized functional. In this reference, we have to do a lot of algebraic manipulations and then we can realize this transformation. And there's a whole heap of algebraic derivation in there, which is quite tedious and fairly complicated to apply. Whereas in here, the problem of estimating delay stack is basically a particular case of the generalized functional. And so if we pick the matrices F and FD accordingly, in this case, it is picked according to this situation. That would mean that the observer that we want to estimate, which is this generalized functional, we estimate the delay unmeasurable stack variables directly. Now that is not through the method apply estimate the instantaneous unmeasurable variables first, which is not possible if we employ uh, other methods like without internal delay. Then we have an unstable observer. Now, if we just apply in our design method, and then we employ an observer without internal delay, as we discussed previously in this topic, part 1, where we obtain the existing conditions, and then we say that we can put all those metric equations stuck together, and then we derive the if and only if condition for the existence of the observer parameters. And then if we can then ensure that the observer is stable, which is the second bit of the existing condition, then we can systematically obtain all the parameters of the generalized functional observer. And for the case when we say we wanted even similar structure without internal delay, then we have a condition where this matrix here has less number of rows than the previous matrix. The previous matrix has this block row in here, and if we don't want internal delay in there, we remove that. So that gives us a bit more conservative existence condition. However, if it's satisfied, then the observer that we obtain would be an observer without internal delay. And so if we apply our method and we just substitute and check this condition, we found that it's actually satisfied. And we can assign, the other thing is that we can assign the eigenvalues of the metric n anywhere we like, because the when we solve for the solutions in here and when we using the extra degree of freedom in this matrix here, we can actually have the pair n1 and n2 observable for this example. And third, we can assign the eigenvalues of matrix n anywhere we like. By the way, it is an observer without internal delay. So the error dynamic equation is just simply this bit here. So it's actually independent of the time delay here. Now, so we basically say that, look, if we want to deal with the issues of design delay version or of the unmeasurable stack variables for this example directly, we can apply our generalized functional observer design method. And it's just a matter of picking the correct F and FD matrices and then applying our existing condition. And if it's satisfied and if it leads to a stable error dynamic equation, then we basically complete the design without unnecessarily going through a whole heap of um, tedious algebraic manipulations. So that's the key there. So let us go back to this numerical example and let us have a look at the codings that we actually implemented for this numerical example. So we have the matrix A, ID, B, and C given in here. And then the one that follow it, see basically testing to see if the conditions of the an existing methods, whether it can give us an observer without internal delay, and that observer is actually the one that estimates the unmeasurable stack variables instantaneously, not the delay version of it. And if we apply this method in, we will find that the the matrix N1 itself, or the reduced order observer, which is a third order observer, resulted in an unstable system, an unstable observer with a pole equal to 1 in there. And so that's not possible. And and then if we apply our method, which is the one given in here, now notice that we're going to define the FD matrix, which is the one that is the same as the F matrix in this method here, because this was aiming to estimate instantaneously the unmeasurable stack variables, but now we say that we have to estimate the delay version of it directly. So this is basically the condition. And so we just apply the existing condition from here, which is the matrix OH, we call it. And OH is the one that is given in here, which is this matrix. So let's have a look at that. So we have OH is F, FD 0, and C tilde 1, 0, 0, and all of that. And then the other matrix we call GH is basically this this matrix here. this is the one there, f time I bar 1 and so on. So we apply our existing conditions for the one without an internal delay, and then we work out the rank condition, which is this condition in here, and then we obtain a freedom in the generalized solution of that equation. And then we exploit it, and then we found that the pair n1 and n2 is observable, and we basically pick arbitrarily the poles of the reduced order system observer, and then we obtain um, a metric L which place the eigenvalues at anywhere we like, and then we obtain the final solution which taking into account of that extra degree of freedom. And then the rest of the observer parameters, as you can see, can be done systematically and fairly easily. So let's have a look at that. So we bang it in, everything in, and then we work out the metric n1, metric n2, and then we work out the general solution. So basically we have the metric n. Now we see the observer aerodynamic equation, and we can assign it at -5, -6, -7, which is the one that we put in here. Of course, we can put any other location. So the main thing that we like to say in here is that when it comes to realizing design a delay version of the stack vector directly, as is in this numerical example, instead of applying the methods presented in this reference, we can actually use the new way of solving generalized functional observers. And in this approach, which we demonstrate in here, it can be done. It can be done fairly easily, systematically. Okay. So this example is basically telling that generalized functionals and the design of generalized functional observers for this system is a novel way to go. So let us look at another example. And in this particular example, which is the one considered in the book, in this example, which is example 3 in chapter 13, where we want to demonstrate the generality of our generalized functional observer for this class of time delay system, which is this one here. We want to really demonstrate the significance of having that extra term in the generalized functional observer design for this linear time delay system. Okay. Now we know that in the past, people look at this class of time delay system and normally estimating a generalized function of it. No, only a function of it, not the generalized function. So we want to demonstrate the generality and the significance of this new generalized functional observer. And so let's consider matrix A bar 1, 1, A bar D 1, 1, B, and C. Now here, this matrix C1 tilde is a canonical form, and it has two measurable stack variables, which are basically the first two of them. And then there are two unmeasurable stack variables, number 3 and number 4. And let's say that we want to estimate these unmeasurable stack variables. And so what are the options available? The option available is that there are already existing methods available. For example, in the Rouge 2001, and also in another uh, paper, which is in this reference in here, it's also dealt with a more general structure, and it's also dealing with estimating a linear functional of the stack vector. Now, let's say when we apply either one of them, one of those methods, what we found is that that is the problem equivalent to selecting matrix F according to this structure, because we want to estimate the last two unmeasurable stack variables in this stack vector. And so that is the functional observer in the existing literature. And that means that FD here is 0. So basically we ignore that bit. And if we want to estimate an observer to estimate these two unmeasurable variables, that is the bit there. And that means that there are existing methods available in the literature, including, for example, Daruch, NAMS, and even Howe and his quote in 2002, and so on. And so if we want to, let's say, if we desire an observer, we always like to go for the one with the seamless structure. And let's say that we aim to design an observer without internal delay for the sake of simplicity. And the attractiveness of it is that this is independent of the time delay when we deal with the error analysis of the error, which is independent of the time delay. Okay, so according to the condition in there, we can test it, and it is satisfied, but it gives us an unstable observer. All right, so here is what I like to show in the codings. So that where we look at example 3. And so we're going to pick the matrix A, B, C, D, and then we apply the conditions in this reference where we are looking for a second order observer without internal delay to estimate the two unmeasurable variables, 3 and 4, instantaneously. So as I mentioned before, when we apply this method, the issue is that the freedom that we have in there is basically nothing in there, and as a result, we have a fixed matrix n, which I call n the root here, and then when we look at the eigenvalues of this matrix, it's give us two unstable poles. So we basically having problem in here, right? So that means that to estimate the two stack variables here using this observer without internal delay, second order, we having problem. And the same thing for the methods by NAM as well. The methods for NAM as well, and that reference is actually the reference given in this book here. We see this reference in here, where we basically introduce an additional delay term in the observer, and then we show that it's actually less conservative than the Rouge condition. But still, in this reference, when it comes to realizing an observer without internal delay, it's also doesn't work as well. So if we apply in the existing condition in there, and we also find the same thing because we got two unstable fixed mode, and as a result, this n1 here is this thing, and this n2 here is basically no freedom in there. So we left with an observer which which has the metric n exactly the same as the rules approach method, and we still have two unstable fixed modes in there. All right, now it's come to the next very important bit, and that next important bit is what to do. Now, if we still insisting that for whatever reason, maybe the customer desire wants that, look, I will pay it at no cost, at any cost, sorry. I like to have an observer without internal delay. That is because in terms of practicality, the aerodynamic equation is independent of the time delay, or for whatever reason it is. And we still insisting that is it possible to realize an observer without internal delay to estimate these two unmeasurable stack variables. And so, you know that in the literature, there is an option that one can do, and that option is to insert an additional row or inserting additional function in to increase the order of the observer. And that approach is called the augmentation approach. The augmentation approach is the one that was first introduced in this reference, where we look at the functional observability and the desire of minimum order functional observers. In that particular reference, we insert additional functions to ensure the satisfaction of certain existing condition, and to relax the requirement that sometimes the necessary and sufficient condition for the existence of the solution does not exist. It would exist if we insert an additional row in this functional, and that therefore relax the existing condition. And that's the idea behind that. As well as that, we also look at the insertion of additional function. We call it Z extension there for a class of time of linear systems with unknown input. So the idea there is, okay, if we can't have an observer with a second order, if we can't have an observer with a second order, then we might increase the order. We increase the order of the functional observer. And to increase the order is achieved by adding an additional functional. Now, in this particular example, we notice that, or it's very important to stress that the matrix C tilde 1 itself is a metric of dimension 2 by 4. And the metric F itself is of dimension 2 by 4 as well. So when we look at this matrix here, it is a 4 by 4 matrix, and this is already of full rank. So what does mean that? It means that if we add in another extra functional to increase the order of observer from 2 to 3, that extra functional itself, that extra row itself is in fact just a linear combination of this existing available output measurement and this original functional observer. So because of that, we basically can't overcome the existing the conservativeness of the existing condition. Sometimes when we test this condition, for example, we might find that the condition does not satisfy, and it might be satisfied by adding extra row in there. Extra row in there would then ensure that this matrix here might become a full rank matrix. And when it's a full rank matrix, this is also a full rank matrix as well. But in this situation, because this condition is already satisfied, and adding a row does not provide any extra degree of freedom in this condition in here. So if we want to estimate extra functional, that extra functional itself is just basically a linear combination of the existing original functional and the output measurement. So, and that is where the problem is. So if we increase the order, it doesn't work. And the same thing for the method by NAM as well. And this is a very important point that we would like to mention it in here. So this is just a demonstration just to show that, look, because the matrix C tilde 1 and F is already a full rank matrix. Adding an extra row here is basically, we said that we add in an extra row, so we increase the order of the desired observer from second to third order observer. And that's exactly what happened in here. So we then retest the condition. So we retest the condition, and we basically obtain a pair of matrix N1 and N2. Now the issue with this situation here is this pair N1 and N2 is not observable. So in other words, we still facing the problem that the design observer for a third order without internal delay also does not exist, okay, because this is not observable. So when we look at placing the pole somewhere, it's not possible because it's not observable, or not even it detectable as well. So like when we just check the eigenvalue of matrix N1, we can see that these two fixed poles, they still remain the same for the second order system. And so we have a problem. And that is the reason, the explanation behind that. When we have already reached full rank in here, and if there is not exist an observer with that or for that original functional, increasing or adding further additional rows or additional functionals does not work. And the same thing for a NAM as well. So let's have a look at this. So we're going to check second order. We already showed that without need to know, we got unstable poles, and then by adding this extra thing in there, the same situation also happen. Okay, again, it's just unobservable. Okay, so we can then say very safely, very confidently that as far as this numerical example is concerned, if we want to estimate the two unmeasurable stack variables instantaneously, And if we want to estimate them using a specific observer structure without internal delay, existing methods in the literature they don't work. They cannot be applied to this numerical example because we got this situation where we have unstable fixed poles in there. Okay, so what can we do? If we still insisting that an observer without internal delay should be the preferred one. So this is basically our approach and the generalization and the generality of our generalized functional observer come in. Now again, if we just do the one second order observer using our method, we also suffer the same issue. So here is what happening. So if we do our new condition in the new book for the case where that one is 0, of course, this situation here, FD is also 0, F is the same one, the condition there is still there. We also having the same problem. We also having the same problem. And the problem is, okay, we need to because I clear up all the stuff in there. So I need to put the original matrix in and all of that. So maybe I can just copy the whole thing, go all the way until our method second order without internal delay. The the one that we have in here in our new condition is that we're going to get again the same problem. We got the unstable poles, which exactly those two fixed poles. All right, so what can we do? And this is the significance of our work, and this is the point of difference compared to all the works in the literature. Now, what happening here is we can indeed increase the order observer. We can. And the reason why we can is that when we look at this new thing here, if we add in an additional delay term or additional delay functional in there, this rank is not full yet. It's still a row matrix. Okay, so I will come back to that a little bit later. So the idea in here is, yes, we can increase the order of our observer. And if we increase the order of observer, we can expand the dimension of our observer from 2 to 3 by adding an extra functional. Now, this extra functional comes from the delay stack vector, and just here, what we like to do is just pick it to be the third stack variable. Okay. Now you might be asking, wow, it is a random pick. The answer will be further explained later on. But at the moment, let's say that we're going to add in an additional functional, and that additional functional is now a delayed stack variable x3. So then what we are saying here is, look, we're going to get an augmented functional. This is now a generalized functional. We call it an augmented vector or augmented functional. And this idea actually came from the augmentation approach, what we did earlier a while ago. Okay, so augmentation approach. we add in an extra functional. And here, that extra functional is the one we call it here. And it happened to be that variable, the x3 delay of it. So that's where it came in there. And this is the original functional. The original functional, which is basically the first, the two variables that we wanted to estimate. We wanted to estimate these two variables. We couldn't do it because it's resulted in an unstable observer, a second order unstable observer without internal delay. And we said, look, we're going to estimate a bigger functional, generalized functional. That's no longer two functionals, but it's going to be three. Okay. And then once we can estimate this augmented generalized functional, of course, to realize these two there, it's just a subset of that one. We just pick the first two of it. And that will give us this estimation there. So the idea here is very clear. We add in an extra functional. And then we call this augmented generalized functional no longer two functionals, but it's going to be three functionals. The thing about that is the last one is really a delay stack variable, x bar 1, 3. And so if we express this in terms of this notation here, then you can see clearly that the new matrix here, we can call it Fi, or it can be just simply be F of our generalized problem. But this is just so that we know that we actually having an additional row in here, additional row in here. Now have a look at FID. The first two rows, they were 0 because that where that two unmeasurable stack variables, x bar 1, 3 and x bar 1, 4 there. This last row here is the addition of this extra functional. It's not instantaneous, it's actually delay version of it. Okay, right. So we then say, oh, how significant it is in terms of really allow us to realize an observer to estimate the two variables without using an internal observer. So the answer for that is as follows. So once we got this new Fi and Fid matrices, we're going to design, now we're going to design a third order observer, because that is consist of three functional. So we're going to design a third order generalized functional observer to estimate this generalized functional, which is this one here. So as you can see that these two matrices now they have dimension of 3 by 4 and 3 by 4. Okay, so what we do, we then say, no problem at all. We're going to replace F and FD in condition 2, where's condition 2, which basically came from the topic 1, topic 5, part 1, where we obtain a generalized condition, which is this one here. So we replace F and FD by FI and FID. Okay. So we replace them by that, and we test the existence condition. We test the existence condition. I don't know where this number 2 came from. It must be somewhere, but I hope that you follow what I'm talking there. So that condition 1. And then now the good thing about that is when we actually do it, that condition is actually satisfied. that condition is actually satisfied. Condition is actually satisfied. So this condition here is actually satisfied. And we are able to design a third order generalized functional observer. And the good thing about that is the eigenvalues of this observer, which is a third order observer now, can be arbitrarily assigned anywhere in the S-plane. So how significant is this? How significant is this? Where in the previous approach, we increase the order, but when we increase the order, it's just an arbitrary row which does not contain any delayed stack vector. It doesn't work. It doesn't work that way. Now it actually works because this is a generalized functional. Um, and the condition itself is satisfied. So I like to show the design of that using the MATLAB codes in there. Okay, so that one now we're going to open another MATLAB code, and this is the one, the complete one with simulation as well. So now the codings in here is using our generalized functional. We design a generalized functional observer with our internal delay. We're going to do it with a third order observer. And to achieve that, we introduce this extra FD, that's the extra row that we discussed earlier. So we got the metric A, B, C tilde, and this is the original F matrix. But now we have this, it's going to be a 3 by 4. So this is the row, the last row there is all 0. The FD that we add in is just simply that extra row in there and just pick up the extra delay variable x bar 1 3 t minus tau. There you see. And so our F and FD basically that. And then we just basically test the condition. We see the condition rank of this matrix and rank of this augmented 2 of that had to be satisfied. And if it is satisfied, we get a solution in terms of this extra degree of freedom matrix. And then we pick from there the pair N1 and N2. And then it turned out to be observable. So we can assign the pole anywhere we like. And then as a result, we obtain the solution, including this solution that enable the metric n stable and the eigens anywhere we like. And then from the solution, we just pick out all the observer parameters. And then we realize or the rest of the parameters, and we can also check the conditions and so on. So let's run this. Let's run this, and that coding is basically based on the development of topic 5, part 1, which is chapter 13 in our book. Okay. So now I clear it and I run it, and there you go. The conditions, they all verify. They are basically 0, and we obtain the metric n1 and 2, and the beauty about this is that it's observable. It's observable. So that's why when we look at the eigenvalues of n1 minus L times n2, we assign them at where did we? we, oh, sorry, what's that? So we got that, and then we pick the, yeah, this is called Z, not L. Sorry about that. So when we look at the eigenvalue of this Z, that where we got the poles at -3, -4, -5. So the thing about this is that with this additional general functional, which is just a simple delay of the stack variable in there, we are able to design a third order observer without an internal delay to estimate this generalized functional. And since we are able to come up with a third order observer without internal delay to estimate this vector I highlight here, of course, we can extract from there the estimation of these two unmeasurable stack variables from the third order observer. How about that? And as a result, we got this metric n, this metric nd, of course, and this metric z, and so on. So that's exactly where we get the rest of the observer parameters. Okay, the rest of the observer parameters. And looking at that is such an amazing result that we can see here. All right, so we realize that this extra function, and then we're able to obtain a third order observer. And these are the rest of the observer parameters, which what we obtain from here. So for example, if we call, let's say G, it's actually it down here, and then GD, and then GDD, and so on, and then M and all of that. So we're able to realize a third order observer without an internal delay to estimate the two unmeasurable stack variables. Whereas the other method that did not use the new concept, which is called the generalized functional, it will fail to work. Okay. Now, the simulation is as follow. So let's cut and paste the rest of these codings in there, and we're going to run simulation, and we're going to show the simulation of the stack variable x3 is the one, it's called x bar 1 3, and it's estimate. Okay. And so maybe I can take all of that, and then let copy and paste it into MATLAB. And we can see that we are able to asymptotically estimate the unmeasurable stack variable x bar 1 3 using a third order observer without internal delay. And this system itself is an unstable time delay system. So when we look at the simulation result, you can see that it's explode to infinity very quickly. And that's why this simulation is shown for a smaller time range. We can even look at the error difference between the two of them, which is the error dynamic of the first difference between the first variable and its estimated variable. There you can see that the error here goes to 0 there. That bit there asymptotically go to 0. Okay, so as you can see, the significance and the generality of just having this generalized functional and how it can do to realize observers with higher dimension. We always use to the idea that the observer should be low order, but there are situations if we insisting that we want a particular specific structure, and so in here, this additional delay term in this generalized functional really can help us to relax the existing conditions. Okay, so we have another option. We have another option because just like in this example, if the internal delay observer does not exist using these existing methods in the literature, the other option is to look at the one with an internal delay and therefore realizing it where the error dynamic equation is dependent on the time delay and so on. Now, the other bit that is also equally important that we like to mention in here is that we can actually pick other combination and another extra functional. This extra functional is not like the third one, is not like the one that we pick it in here, but there is another functional which is the delay of the variable number 4. And even if we do that, it also works as well. It also works as well. So I don't know whether I actually have that. Yeah, this is the one that with this extra functional is picked to be the last variable, the delay variable. And therefore, as you can see, all we do is just replacing this FD by that. And then if we go through the whole process, going through the design, which is very systematically, the condition is satisfied, the pair is observable, and therefore we obtain a third order observer without internal delay using that alternative extra functional. So we got another possible way of picking the extra functional. So here that all works, and there you go. It just asymptotically go to 0 there. Okay. Right. So this is what we mentioned in here. All right. We can. So now the thing here, this is the summary, the statement that we want to stress here. This is for the first time. By a novel idea of estimating an additional delay function of the stack vector. We can expand the dimension of our observer without internal delay to achieve asymptotic estimation of the original required function. Now, the idea of doing this stuff is come from, which is basically we can think of it like an extension of the augmentation approach available in the literature for that was done for linear systems without time delay. This was done for linear system with unknown input. The idea of increasing an extra functional came from these references. We can think of this like an extension of augmentation approach to deal with time delay system, right? Now, the key open research problem, which we would like the reader to investigate is the following. What would be the how to systematically find a matrix? Now, we just demonstrated that we pick this matrix, just one single row with an extra single row there, and we just pick it to be a non-zero element in here, which is the last stack variable, the delay last stack variable, or the other case where we pick a non-zero element in there, which is that one there. We just pick them. We didn't show how you systematically pick them. Yeah, but we demonstrate the generality and the extra degree of freedom that this extra functional can actually add into the existing conditions. So the problem that we would like the reader to investigate in the future is how to systematically find a matrix with the minimum dimension, because sometimes you might find that might need to add in more rows instead of just one row, and that where in this reference we show that there is an upper bound number where we can satisfy a certain condition, and then we test the other condition and so on. There, there's an upper bound for it. But how to find it with a minimum dimension? How to systematically find it with the smallest integer? So in other words, we want it the least number of additional rows that we want to add into in order to achieve the satisfaction of the condition, which is this condition here. Sometimes when we do the design, we test this condition, we find that it's not satisfied, and then so we have to add in additional rows to the existing functionals, generalized functional, add more rows. What would be the minimum number of that? And once this is satisfied, we still not out of the wood yet. We still have to ensure that the error dynamic equation is stable. So this is the key issue that that needs further investigation. And so we want to find a systematic way of finding this extra matrix, or even talking about the entire additional in terms of the instantaneous as well. In this situation, we pick this one because C tilde 1 and F is already full. So that's why there was no point. Just add in a combination of the instantaneous stack vector. And that's why we just basically find this extra rows come from this delay stack vector. Okay. So we want to know that what will be the minimum number and how to ensure stability. And that is something the reader can further investigate. Okay. Now the other question is, okay, when you increase the order, like for this particular situation where we are dealing with the one without internal delay, the question is, do you keep increasing the order with the hope that that will result in a stable observer? The answer is sometimes we keep increasing it, but doesn't mean, it doesn't guarantee that the observer is still stable. You see, and that means that there must be an underlying condition on top of the condition that we discuss in here, which is this condition, and of course that's it, because we want to ensure stability of the error equation here, and that comes from the detectability or the observability of this pair n1 and n2. We could have derived an assistant condition to guarantee that the detectability or observability condition is satisfied. But in our analysis discussion here, we didn't delve into it because we just like to make the discussion simple. We say, okay, we test this condition, and if it is satisfied, we go on to obtain this aerodynamic equation. And if this aerodynamic equation is stable, in other words, the pair is detectable, observable, we could have come up with another condition, that can be tested before we keep on increasing the order of the observer. And so that can also tell us that, look, there is a problem that we can solve, and which is following the idea of this reference. And by the way, there is a latest work appear in archive that talk about the unification of functional observability and functional controllability and all of that. What we can do, we can then say, okay, we might be able to develop a generalized functional observability condition for estimating generalized functionals of time delay system. Okay, so there are issues, there are things that can be further investigated, and we just like to leave it to the reader to further investigate. What we have demonstrated so far in here is that with this extra degree of freedom, we can expand the dimension of the observer. Remember, it's going from 2 to 3 now. Whereas without this extra delay term in the generalized functional, we stop at second order observer without internal delay. So we couldn't have any other option to realize the estimation of these unmeasurable stack variables using an observer without internal delay. Whereas now it is possible. Okay, so that's the thing that we like to stress to the reader. And finally, when we got all these generalized functional observers, we can actually use them to estimate the unknown input. So as far as chapter 4 is concerned in the book, where we was discussing about the asymptotic estimation of an unknown input for a time delay system. So for an unknown input for the time delay system. And then when we look at it, we say, okay, it would be nice to be able to realize this generalized functional directly. And that was the discussion in scenario 4. We want to estimate this directly so that we can have a much simpler or a better way of realizing the unknown input. And remember, that was done for this particular class of time delay system. Okay, for this particular class of time delay system, where we apply the decomposition to obtain this class of system with an unknown input time delay system. And when we do our decomposition, we arrive at this time delay system, and we need to estimate the generalized functional. So we can actually do that now. Okay, and so simulation. Let's show the simulation as well. Let me try to find out where that is. Maybe this example 3. Yeah, in this example, we got the matrix itself. We obtain an observer that we estimate the delay stack variable directly, and then we apply that, and then we realizing this unknown input. And this one is actually the one that that was shown in this chapter 4. In this chapter 4, example 6. And just to remind everyone in chapter 4, example 6, scenario 4, this is the one. Uh, we arrive at this unknown input decomposition, and we require to estimate the unknown input by estimating this delay stack variable directly. And we could do that. And when we did the simulation, the observer is this one. Okay. Observer is this bit here. As well as we also have the simulation. Okay, let's get rid of this thing. And we also have the simulation of the design of the delay stack variable directly. Okay, so everything can be seen. We can see that everything now fit in nicely. The need for design generalized functionals is very clearly demonstrated in this book. And to design a generalized functional observer is a new way of doing it, because in the literature nobody came across this issue yet, and that's why we found that there was no discussion about that generalized functional. And now we demonstrated that the design of generalized functional is much more general, and it can also relax existing observer conditions. Okay, so that basically wrap up this presentation part 3, topic 5, and I hope that can give the reader some motivations and ideas for further investigation into this new generalized functional observer design problem, as well as there are issues, things that need to be done, like, for example, how do you find a systematic way of adding this extra number of rows in there? Can we ensure stability or detectability of the pair of the error dynamic equation? Maybe there should be another investigation into the generalized functional observability condition for generalized functional observers of time delay system, something along that line. Okay, so thank you very much for watching. And the discussion today is around sections 11, 13.1, 13.2 in chapter 13. In our next video, we're going to go into topic 6. Now, in here, we will discuss the design of generalized functional observers for this time delay system. Now, when we look at this time delay system, the only difference, this one and the one in topic 5, is that in topic 5, we don't have the delay term in there. We don't have it. In this new topic 6, we have it. And where is it came from? It actually came from the decomposition in chapter 5. So if we look at chapter 5, where we look at this time delay system with this extra delay term in the output measurement, and if we follow the decomposition technique and we impose a constraint on it, and then with that particular constraint, we arrive at a reduced order time delay system without a known input, which is this one here. And as you can see, it has an extra term in there. As well, the decomposition of the unknown input is now in terms of this generalized functional. So there's a need for the design of generalized functional observers to estimate this generalized functional of this new class of time delay system. And that's what we aim to do in topic 6. Okay, so thank you very much for watching, and I hope to see you again in the next video. Thank you. Bye bye for now.